Welcome back. Today we are learning about inverse relations and functions. Inverse relations are inverse if one relation contains elements of the form AB and the other, the inverse one, contains BA. So basically, notice we're just interchanging the x and y value in that ordered pair. Not all functions have an inverse function. If a function fails the horizontal line test, you can restrict the domain of the function to make the inverse a function. Choose a portion of the domain on which the function is one-to-one. There may be more than one possible domain. So taking a look at example 1, we've got the vertices of triangle ABC can be represented by the relation 2, 4, negative 3, 2, and 4, 1. Find the inverse of the relation, graph both and the original relation and its inverse. So first we're going to graph the ordered pairs and connect them to form a triangle. So 2, 4, I would go right 2, up 4, and I will put a point. The next vertice is at negative 3, 2, so I go left 3, up 2, another point, and then lastly 4, 1, go right 4, up 1, and then we'll connect them. Next, we are going to interchange the x and y values. So we're going to switch the 2 and the 4, so that becomes 4, 2. Negative 3, 2, we interchange them, that becomes 2, negative 3, and then 4, 1, interchanging becomes 1, 4. So now I'm going to plot those points. So 4, 2, 2, negative 3, and then 1, 4. And we will connect them. And then that is the inverse triangle. All right, so to find the inverse of a function, so we have a linear function here, f of x equals 3x plus 2. We're going to first replace f of x with y. So it becomes y equals 3x plus 2. Then we interchange x and y. So it becomes x equals 3y plus 2. And then we're going to solve for y using inverse operations. So I'm going to subtract 2 from both sides, and then divide both sides by 3, so we get y equals x minus 2 over 3. So then lastly we're going to replace f of x, or replace y with f inverse of x. So that's how we would read this notation here, f inverse of x. To graph f of x, it was in slope-intercept form, so our y-intercept is 0, 2, so I would start there, and the slope is 3 over 1, so I'm going to go up 3, right 1, and then you can also go down 3, left 1, and connect your points with a straight edge. Now to graph the inverse function, the slope is 1/3, but the y-intercept would be negative 2/3. Since that's not a whole number, I just looked at this point here, which is 0, 2, and if I interchange that, it becomes 2, 0. And then the slope of 1/3, so it can go down 1, left 3, and connecting them. When we look at example 3, we have a quadratic function, f of x equals x squared plus 2x plus 4. So, and here it is graphed. You can see that it's not a one-to-one function, because if I were to draw a horizontal line, it would intersect it more than once. But we can still find the inverse of this function. So we're going to, again, replace f of x with y. That's our first step. Then we interchange x and y. So now to solve for y, it's a little different than solving for y when it's a linear equation. What we're going to do first is subtract 4 from both sides, okay, and then I left a space here intentionally because we are going to do what's called completing the square. So over here where we've got y squared and y, we have both a quadratic term and a linear term. I can't solve it just using inverse operations, so we're going to do completing the square. So I'm going to try to create a perfect square trinomial on the right-hand side here. So what's half of 2? That would be 1, and then 1 squared is 1. So when I add 1 here, that completes the square. I have to add 1 on the other side, because whatever we do to one side of the equation, we have to do to the other. So this side, if I were to factor that, I would factor into y plus 1 times y plus 1, or y plus 1 squared for short. And then on the left-hand side, combine negative 4 plus 1 to get negative 3. Now we're trying to isolate y, so to get rid of this square power, I take the square root of both sides. When we take the square root of both sides, we have to remember plus or minus. So really we're getting two answers over here. That's why you can see two different functions graphed down here. Last step to solve for y is subtract 1, and then replace y with f inverse of x. All right, so then because there's the positive square root of x minus 3 minus 1, and then the negative square root of x minus 3 plus 1, you get two separate functions here. If the domain of f of x is restricted to negative infinity to negative 1, then the inverse of f of negative 1 of x equals negative 1 minus square root of x minus 3. Or if you restricted it from negative 1 to positive infinity, then it's f inverse of x equals negative 1 plus the square root of x plus 3. So you have the different functions depending on which one you restrict the domain to. All right, in example 4, we have a formula for converting a temperature in degrees Fahrenheit to degrees Celsius. So the temperature of x equals 5/9 times the quantity x minus 32. Find the inverse. Okay, so I replaced t of x with y. Next, we're going to interchange the x and y. When you're performing inverse operations, you actually want to start outside of the parentheses first. So outside of the parentheses, we're multiplying by 5/9. The inverse operation would be to multiply by the reciprocal. So I'm going to multiply both sides by 9/5. So the 5/9 times 9/5 cancel each other out. And then lastly, to get y by itself, we have subtracting 32 from y. So the inverse operation of subtracting is adding. So I'm going to add 32 to both sides. And then I would replace the y with t inverse of x. And since the original formula converted temperature from Fahrenheit to Celsius, the inverse will convert from Celsius to Fahrenheit. We can verify functions are inverses of each other if their composition of functions equals x, or y equals x is called the identity function. So recall back to section 6.1 on how to find composition of functions. So our function here, h of x equals square root of x plus 13. K of x equals x minus 13 squared. Are they inverses? So composition of functions means, so to find h of k of x, I'm going to go to the h function, and in place of x, I'm going to put parentheses. And then what I will input in the parentheses is the k of x function. So k of x is defined as the quantity x minus 13 quantity squared. So I'm going to put that where there was x. To square a binomial, we square the first term, so that's x squared. Then I multiply these terms together, which would be negative 13x, and then double that, so negative 26x, and then square the last term. Negative 13 squared would be 169, and then I bring down that. Combining like terms here, 169 plus 13 is 182. So this is as simplified as I can make that expression by squaring the binomial and combining like terms. But this in simplified form does not equal just x. So these are not inverses of each other. All right, example 6. The formula for the volume of a cylinder with a height of 5 inches equals V equals 5 pi r squared. Determine whether r equals square root of V over 5 pi if that is the inverse of the original function. So we'll do the composition. So first I'm going to find V of r. So go to the V function, and we're going to be replacing r with this definition of r, square root of V over 5 pi. All right, now to simplify this, the square power and square root are inverse operations, so they're going to cancel each other out. Then multiplying by 5 pi and dividing by 5 pi, multiplying and dividing are inverse operations, so they cancel out. So we did end up with the identity, back to volume. And then we also have to do the composition in the other order, so r of V. So if I go to the r function and I'm replacing volume with 5 pi r squared, the way volume is defined. We'll see what happens. So starting inside the radical, 5 pi over 5 pi would cancel out. And then we've got square root of r squared. Square root and square power cancel each other out. So these are inverse functions of each other because the composition equals the identity function. Thank you for watching.